This video is over lesson 8.0, which is an introduction to sequences. We're going to focus on looking at patterns and numbers. This lesson is kind of the foundation for the rest of chapter 8. We're going to look at certain vocabulary words and notations we're going to use so we can get more comfortable with them, and then work on identifying patterns to help us build our understanding throughout this chapter. So the first vocab word we're looking at is term number. Now, term number is a number that gives the position of a term in a sequence. So a number that gives the position of a term in a sequence. And we represent it as the variable n. And we refer to it, and we'll get into this more, as the input. When we're dealing with a table or if we're dealing with a function on it. So the term number is the position. The value at that position is the term. So the term is the output component of a sequence. And for this, we are going to use T of n. That's what we're going to use to represent it. So that's term, which is the value at the position that you're looking at. Term number is the position itself. So sequence is an ordered set of objects. And usually our objects that we look at are numbers on it. And one example would be like the Fibonacci sequence. 1, 1, 2, 3. And what I'm doing is I'm adding the two previous numbers. 1 plus 1 is 2. 1 plus 2 is 3. So then 2 plus 3 is 5. 3 plus 5 is 8. And that goes on and goes on. So that's a sequence of numbers. They're separated by commas on it. Now, a series is the sum of the terms in a sequence. So it's the sum of the terms in a sequence. Using that same Fibonacci sequence, then I would do 1 plus 1 plus 2 plus 3 and so on, plus 5 plus 8, and that would go on, and I would find what is that sum. So a sequence is a set of numbers or a set of objects that we're looking at. Term number is your input, term is your output. So as we go through this introduction, what we want to do is we want to kind of look at what are the patterns we're going to see, how can we describe them, what do they have in common, how does the sequence grow. So in the first set that we're given, the first sequence. Now remember, n is your input, it's your position. T of n is your output. It's the value. So the first position, the first term, the term number for 1 is you have is -4. The second position is -1. The third position is 2. The fourth position is 5. So we look at it based off position and the value at that position. And so that's our sequence. If I were to plot these on this graph, at 1 I'm at -4, at 2 I'm at -1, at 3 I'm at 2, at 4 I'm at 5, I can start to see that there is a pattern in what we're doing on it. I should be able to find the rest of the numbers, and I can look at it just from the table. How do I go from -4 to -1? Well, I can check. Well, I add 3. -1 plus 3 is 2. 2 plus 3 is 5. So I can keep on following that pattern. So the fifth term should be 8, and the sixth term should be 11. So at 5 I'm at 8, at 6 I'm at 11. Looking at it visually, I see this looks like, and I'm not going to graph it, I'm going to erase it afterwards, but it looks like it follows a linear pattern on what we're dealing with. So my pattern is I'm adding 3 each time. And because that is a constant rate of change that I'm dealing with, I'm looking at a linear pattern for it. So it's a linear pattern which tells me I have a constant rate of change. Which we refer to as slope. And so my slope is 3. It's actually the same as what my pattern was. I was adding 3. My slope is 3 for this. And so I can use this to write an equation because it's linear. Because it's linear, we have the equation for slope intercept form, y equals mx plus b. But we're not dealing with y or x. We're dealing with n and t of n. And so we have to realize, in this case, y is your output. X is your input. So if I were to think of this with the vocab we're using and the notation we're using for sequences, output is t of n. My slope, which will change when we learn 8.1, but I'll use m to be a little consistent on it. My input is n. And then I'm going to leave this here as b. Now b represents the y-intercept in slope-intercept form. So the question is, what does it represent here for it? And so if I look at, well, I could see a slope, so if I wanted to, I could go backwards. I could go down 3, left 1, in order to find that y-intercept. Or I could think of from the table, if I'm going backwards, I'm going to do the opposite. I'm going to subtract 3. And so this right here would be -7. And we refer to that in this chapter as the zero term. The zero term is -7. And that's really what your y-intercept would be. So we consider this our zero term. And the reason why this is helpful is we can now write the equation. Because we recognize it follows a linear pattern of a slope of 3. My input is n. My zero term is -7. And so there is my equation of that sequence for it. So we look at the table, we look at the visual aspect of it, and we think about the structure that we're used to already with slope intercept form, and we can go from there. Now for number 2, let's look at the table. First term is 1.5. Second term is 3. Third term is 6. Fourth term is 12. So as I go through this and I want to find what's the pattern for it, I can keep on filling in, okay, well, what's the 5th term and what's the 6th term? Well, it doesn't look like an addition pattern because 3 to 6 increases by 3, but 6 to 12 increases by 6. There's no addition pattern, but if I look at it, from 3 to 6, and then from 6 to 12, I'm multiplying by 2 here, I'm multiplying by 2 here. That's a little bit easy to see. Let's check the other ones. If I look at 1.5 times 2, I do get 3. So that looks like that might be my pattern. I'm multiplying by 2. And so the 5th term should be 24, the 4th term should be 48. Perfect. So let's graph them. Looking at my scale, it looks like each grid box is going by 2 on the y-axis. So at 1, I'm at 1.5. The second term should be 3. The third term should be 6. Fourth term should be 12. And then I should be at 24. And then 48's off the grid. Well, if I look at this one is not linear. There's a curve to it. This, since we're multiplying, think about it, you're times by 2, times by 2, times by 2, times by 2, times by 2. That's annoying to say. I could say that's 2 to the 5th if I look at the table. So we call this an exponential pattern. because you're multiplying by the same number every time. There is a constant multiplier, and in this case that is 2. Now the structure that we used before for exponential functions is y equals a times b to the x. Same exact idea. Y is your output, x is your input. And so if I want to transform this, my output is t of n, my input is n, so I still have this a, this b, and my n is my input, so that's nice. The question is, what does each one of these represent? Well, b is the base that you're dealing with. It's what you're multiplying by. It's like 2 to the 5th, if I look at this column. Or if I look at the first 2, 2 squared, or 2 cubed, or 2 to the 4th. And so b here is your multiplier. A is your 0 term. It's your starting point. And again, I don't have it if I look at it, but if I know how to go forwards, I should know how to go backwards. If multiplying by 2 goes forward, then dividing by 2 is going to go backwards. So in this case, 0.75. And so I can even plot that here. So we'll say that's 0.75. So I can write the equation. T of n is going to be my 0 term, my starting point, 0.75 times my power 2 to the n. So there is the equation of the sequence. We're trying to relate it to exponential form that we dealt with before. So let's look at questions 3 and 4. So number 3, I'm going to say kind of fill in my term positions. So this would be 2, 3, 4, and those are given to me. 5 and 6 I'm going to find. The first term is 9. The second term is 7. The third term is 5. The fourth term is 3. Well, looking at this, it looks like each time I am subtracting 2. So this would be 1 and this would be -1. So I have a pattern. I'm going to refer to it as adding -2 to it. So if I'm looking at this and I'm thinking about it, I can figure out my 0 term by going backwards. If subtracting 2 goes one direction, then adding 2 is going to go the other. My 0 term is 11. My 0 term is up here at 11 if I extend this up. And then, let's see, 1 I'm at 9, 2 I'm at 7, 3 I'm at 5. And as I'm plotting them, I'm looking at it and I'm seeing there is a linear pattern to it. I could keep going on this for it. It looks like I'm going down 2, right 1. So again, it looks like there is a linear pattern. We said we're adding -2. You could say you are subtracting 2 on it. And that's your constant rate of change. That's your slope. I have a slope of -2. That's my m. So if I look at this, my equation, remember the structure is T of n equals m times n plus b, where remember T of n is your output, n is your input, m is your slope, and b, the y-intercept, is your 0 term. So I could write the equation. I could say T of n equals -2n plus 11. Done. There's my equation. It followed a linear pattern, so it's really like slope-intercept form. For number 4, my first term is 48. My second term is 24. My third term is 12. I can see right away it's not an addition or subtraction pattern. Here I got to find the next 3. Well, it looks like you can say dividing by 2, but we don't want to say dividing by 2. We're going to say multiplying by 1/2 on it. So we're multiplying by 1/2 each time. So this would be 6 times by 1/2. This would be 3 times by 1/2. This would be 1.5. So my pattern is I'm multiplying by 1/2. And the reason I'm saying multiplying is because that's really what exponents do. This is an exponential form. It's an exponential pattern to it. We have a constant multiplier when you're dealing with exponential patterns. And that multiplier is, in this case, 1/2. We don't say it's divided by 2. We say we're already multiplying by on it. So the constant multiplier is going to be 1/2. So if I'm looking at this, can I find my zero term? Well, if I'm multiplying by 1/2 to go one direction, then I'm going to multiply by 2 to go the other direction. And so that would make this 96. So it looks like we're going by 2's again on this. So at, see, 1, I'm at 48. At 2, I'm at 24. At 3, I'm at 12. At 4, I'm at 6. 5, 3. And then here 1.5. You do see it looks like it's decaying, looks like it's getting smaller on it. So the formula we have here is T of n equals A times B to the n. And in this case, remember, A is your zero term, B is the base, B is your multiplier. So if I want to write the equation here, I have T of n equals, my zero term looks like it's 96, my multiplier. And this is why we write it as what you multiply by is 1/2 to the n. And so there's your equation. So really we just looked at two main patterns, and it's the big ideas for this chapter. We're going to have arithmetic sequences in series, and we're going to have geometric sequences in series. And for arithmetic, there's going to be a constant difference in the sequence. It's going to follow a linear pattern. T of n equals, and I'm just going to refer to it as m for this lesson, times n plus b. Remember, T of n is your term. N is the term number. M is your difference. It's that constant difference that you're looking at. And B is the zero term. You also have geometric sequences, which means you have a constant, we call it a multiplier on it. We refer to it later as maybe a constant ratio in the sequence. And that follows an exponential pattern. And that's the equation T of n equals, we'll use A times B to the n. Same idea. T of n is your term. N is your term number. B is your ratio that you're dealing with. That constant ratio or that constant multiplier. And A is going to be your zero term. So this is where we're going in the chapter 8. So we thought I'd do a little introduction so you can kind of get used to the structure, the format, and the notation on it. The back page of the notes really goes through some interesting numerical sequences that are not arithmetic or geometric. Squared numbers, triangle numbers, and Fibonacci numbers. They're worth kind of looking at and getting used to and seeing them for it. But this is just the intro to 8. Hopefully the idea behind sequences and series